Okay, now what we're going to look at is, now that we've thought about the metals that we need to protect, how do we protect them? How do we protect the bridges and the ships that are in the water, and even the rebar or the metal rods inside concrete buildings and sidewalks and things like that? How do we protect those from corroding away? So, if we take a look at your notes here, you'll see we got a big space here. We're just going to write a couple of different things that we can do to protect those metals so that they don't corrode. Alright, so number one, and probably the most obvious, if you had a piece of metal that you wanted to keep from rusting, you would paint it. Or give it some other kind of protective coating. And the whole purpose of this is to interrupt that spontaneous reaction. So water and oxygen are over here, and iron solid is right here, right? Normally that would be a spontaneous reaction between the two. What we're essentially trying to do, though, is to break that connection, right? If we put a paint or a rubber coating or a powder coat or whatever you want to use, if we interrupt that connection, iron can't give its electrons to water and oxygen, so it won't rust. Now the downfall of that is if you get a chip or a scratch or something in the paint, now your car or your bridge or whatever starts to rust. So it does provide a measure of protection as long as that coating stays intact. As soon as you get a break in that coating, that area is going to start to corrode and break down. So let me give you a different view of this. So this is the website for the Eiffel Tower, if you want to go look up some interesting information about the Eiffel Tower. But one thing that they do is they repaint the entire Eiffel Tower every, I think it's on average, what did they say here? Once every 7 years on average, they repaint the entire Eiffel Tower top to bottom. And because it's a historic landmark, they only use historic methods, meaning paint bucket, brushes, hand tools, no sprayers, no power tools, nothing. So it's just guys like this repainting the entire Eiffel Tower about every 7 years or so. So here's a few statistics. It takes 25 painters, 60 tons of paint, 50 kilometers of safety lines to hold them all up there, 2 hectares of safety nets, that's 4 football fields, 1,500 brushes, 1,500 pairs of overalls, 5,000 sanding discs, 1,000 scrub planes or scrapers, 1,000 pairs of leather gloves, and it costs them about 4 million euros. So it's a huge process to repaint the Eiffel Tower, but if you want to protect it, that's what it's going to take, right? You're going to have to do something to maintain that structure. One thing that I found interesting, I don't know if you guys know this or not, but I don't know where did it show that here. So right here it mentions that the color of the Eiffel Tower has changed over time. Look this up. It's actually really interesting that like it started actually as a red, kind of a really dark red color. Then it turns to a reddish brown, then it's an ochre brown. Now it's kind of then it was a yellowy sort of a brown. After a while they started grading it, so they actually made the color at the top different than the color at the bottom, like a gradient. Anyway, if you want to look it up, it's really kind of interesting. You're bored anyway, I know, trapped at home, but this might be something you could look up. So that's one thing you can do, is you can paint or you can coat that structure to prevent the corrosion from happening. All right. Number 2 is a mild electric current. So essentially, remember that iron in this spontaneous reaction wants to give up its electrons. If we force electrons into the iron, it'll prevent it from giving away its electrons. So think of somebody trying to give you $1, like a loonie, but they were sitting in a pile of loonies. Nobody's going to go swimming through the pile of loonies to take that one loonie if there's just loonies everywhere. So by throwing those electrons in there, we're going to stop the metal from corroding. The reaction can still take place with the oxygen, but it'll just take these free electrons rather than the ones from the iron, so it won't corrode. So let's just put a flow of electrons. Prevents the metal from giving up its electrons. So things like this would be used in underground pipelines. So for example, on a buried pipeline, they might have little stations or solar panels, something like this, and they would provide an electric current. So in this case, the pipe is the cathode because we're forcing, remember electrons move anode to cathode, so we're forcing the electrons into the pipe, which means that the cathode is gaining electrons, not losing them. So in that sense, that part of the metal is protected. And then as the anode, you could use either some metal that you could replace over time, or even something like an inert electrode that would still be able to accept those electrons or that flow, keep it going without causing a change in the reaction. So there's different ways of doing it, and sometimes this one gets combined with the next one we're going to talk about. But so you might have these buried pipelines or things like that where they do something like this. It's just a really mild electric current running through there to prevent the pipe from corroding underground. All right, back to here. Number 3 is what we call a sacrificial anode. So in this case, the metal itself in the spontaneous reaction is the anode, right? It wants to give up its electrons, it wants to lose them. So we want to give it, the reaction, something else to deal with. So typically, if we look at this, you'd have oxygen and water here, and you'd have iron here. So that spontaneous reaction would take place. But if we look at our table, we can give it a different metal that's stronger. So what if, for example, I could say zinc or magnesium. If I attached either of these metals, zinc or magnesium, they're a stronger reducing agent than the iron is. So because they're a stronger reducing agent than the zinc or the magnesium, they're going to react before the iron does. So essentially, let me switch colors here. You have these reactions, whichever metal you use, taking place first. So that sacrificial anode is going to corrode, it is going to react and break down, but it's going to stop the iron from breaking down. So in this picture above here, that's what's going on. So we've got this underground gas tank here, and in order to prevent the underground gas tank from corroding, from breaking down, they've attached this block here of magnesium. So because that's a stronger reducing agent than the iron in the steel that makes up the tank, it's going to corrode first. So all you'd have to do is maybe once every few years or so go down, and they probably have an access hatch. They can grab the magnesium block that's connected, they can take it off and replace it, and in that way that's a lot easier to replace that block of metal than it is to replace the entire gas tank, especially if that gas tank is corroded enough that you've started leaking fuel into the soil and the groundwater and things like that. Now you're dealing with a whole another headache. So let me show you some pictures of this, for example. So in concrete, we talked about that there's rebar there that needs to be protected. Maybe not necessarily in sidewalks, but some buildings are made of concrete, right? Think of a parkade. All of those levels are concrete. If the metal that's reinforcing that concrete starts to break down over time, that's going to weaken the whole structure. So in this case, there are these blocks of, I would assume that's magnesium or zinc or something that's attached, and that's going to make sure that if anything in the concrete breaks down, it's going to be those, and there should be enough there to last a very, very, very long time before the iron ever starts to corrode and break down. A similar thing is done with ships. So these blocks right here on the surface of the ship are the same thing. They're a sacrificial anode. So as the ship is sailing around, even though the hull of that ship is made of steel, and that steel contains a large amount of iron in it, all they have to do every once in a while is pull the ship into dock, lift it out of the water, replace a few of these guys, and instead of having a whole rusted out hull that you need to deal with. Now you notice too that they also paint it. So the ship is coated, it's painted, but you run into things, or it scrapes along something, or the paint just happens to wear out and it chips, then your hull's going to rust. This provides that second layer of protection though. So if anything does start to rust or react with the hull, now it's going to react with these sacrificial anodes first before the iron in the ship. So that's it. We've got 3 different ways that we can protect a metal if we want to stop it from reacting with that water and oxygen. We can coat it, we can provide it a mild electric current, or we can give it a sacrificial anode to protect that thing from reacting. So make sure you know those 3. Make sure you understand the reaction, like what the corrosion of metals are, whether it's iron corroding to turn into rust, or whether it's something like copper oxidizing or silver tarnishing. All of them are essentially the same basic reactions, just a different solid metal that's undergoing the oxidation. So make sure you understand that. If you have any questions, let me know. I think there's only 2 questions in the homework for this one, so it's a really short one, and after that we're into review mode. So if you have any questions about anything, let me know.